Hi, welcome back. In this lecture, I want to talk about unitary matrices. So this is an extremely important topic because it turns out that any matrix that is representing a quantum gate is a unitary matrix. Right? So I really want you to understand why is the motivation for this, right? So why in quantum computing we're going to use unitary matrices. So I will describe the definition, the properties, and I will try to make a link with the quantum computing. So first of all, unitary matrices are part of those invertible matrices. So what is the definition of invertible matrix? Well, an invertible matrix is invertible if there exists another matrix called a to the minus 1. This is like the inverse. If we multiply a for its inverse, then we obtain the identity matrices. So we can both multiply right or left this inverse and still obtain the identity matrices. So unitary matrices are a subclass of invertible matrices. But as a condition sine qua non, must be invertible. So we will see during this lecture that unitary matrices are invertible and their inverse is actually their adjoint. So the main property of unitary matrices is a special one, that transformations that are expressed by unitary matrices preserve the geometry. So for instance, if you have a vector and you have a length associated with this vector, and you apply a transformation associated with the unitary matrices, the length of the matrix will be preserved. And that's why we say that the unitary matrices preserve the geometries of the space on which they are acting. So let's go to the definition. So an n by n matrix U, keep in mind they must be square matrices, otherwise cannot be invertible, and therefore they are not unitary. So a square n by n matrix U is unitary if U multiplied by the U dagger, that is equal to U dagger multiplied by U, is equal to the identity matrices. In other words, the adjoint of the unitary matrix is nothing else than the inverse of the matrices. So it's important to realize that not all invertible matrices are unitary, but only for which the inverse is equal to the adjoint. A very nice example of a unitary matrix is this one. So we have a block that is cosine theta, and then we have two bands here. So this is a unitary matrices, right? So if you multiply this by the adjoint, that is nothing then symmetric and then conjugate. So we have a cos theta. We have the first line becomes the first column, right? So it's minus sine theta, and then 0 here, and then we take the second row and we put here, and take the third row, we put it here. So we multiply this one, you can verify that this multiplication is equal to the identity matrices. So you will need some basic trigonometry identities to verify. But you can do this, as a simple exercise and verify that this matrix here is actually unitary. Have you seen this before? Maybe if you have been working, for instance, on visualization graphics, you will see that, for instance, rotation of the vector is a unitary matrix, and this matrix here represent a rotation of an angle theta of a given vector. So we apply this matrix of a vector, and then we can rotate by an angle of theta. So if you've done visualization graphics course, you might have seen this matrix before. Is unitary, and that means that they can be inverted. so it's also reversible, but most importantly, it preserves the space, so it doesn't change the length of the vector we apply this transformation. The unitary matrices have a bunch of properties, so for instance, they preserve inner product, and this is just a more formal way to express what I told you before in more informal way, that we preserve the space. A more formal way is that to say that unitary matrices preserve inner products. This actually can be easily demonstrated by applying a number of properties that we have been discussed in the previous lecture. So this is more formal demonstration that the unitary matrices and associated transformation preserve the geometry. There is a nice visualization of the unitary matrices that is, we can think as a rotation of a vector all over on one sphere. And the reason for that, since we are preserving the norm of this vector, then this transformation is constrained to move on this sphere here. So this is a nice diagram that expresses the number of matrices and the subclass. So what we are interested in is in this subclass here, that is the unitary matrix here. As we can see, they must be invertible. However, not all the invertible matrices are also unitary. Only the one for which the inverse is actually the adjoint. And because these are invertible, also this must be square matrices here. So why is important that why is important to have unitary matrices in quantum computing? Well, this is related to the fact that operation in quantum computing must be reversible. I repeat this because it's extremely important for the course and is extremely important in our learning quantum computing. So each operation, for instance, each quantum gate and each operation associated to a matrix expressing a quantum computing operation must be reversible. So the reversibility is built in the fact that unitary matrix must be invertible. So for any operation U, any quantum computing operation U, any quantum gate U, there must exist a matrix that can undo, right? That can allow us to go back, as we apply an operation from a certain state, but there must exist an operation to go from the resulting state, go back to the initial state before the transformation. Each quantum operation that we do must be invertible. And because each unitary matrix is also invertible, these unitary matrix express reversible operation. So this is one of the postulates of the quantum computing world, that all the actions that they are not measurement, those are undoable. So they can be reversible, and we can be able, from going from the results, go back for the initial state. So the evolution of a quantum system that is not a measurement is given by a unitary operator or transformation. I talk a little bit about reversibility of quantum computing, on the fact also that the very first step in going towards quantum computing is actually designing gates that are reversible. So starting from the early 80s, there has been quite a lot of work on so-called reversible computing that also led to quantum computing. So a lot of this theory then fed into the building blocks of quantum computers. So remember, if we have a gate the gate must be reversible, and therefore there must be an inverse. In addition to that, we require a stronger constraint that is also unitary, so it preserves the space. So a question for you is that is this not operation that is described by this matrix is unitary? Well, there is a way to calculate that. So we have a 0, 1, and then 1 and 0. If we take the adjoint of this, so that is the symmetric conjugate, then this is the same matrix, right? So is 0, 1, and 1, 0. If we multiply these two matrices, then what we obtain is the identity matrices. So that also means that this operator, so this matrix is unitary, right? Because if we take this matrix, we multiply by its adjoint, we obtain the identity matrix, that is the definition. Another question, this is the matrix that is actually representing the AND gate. And so we go from 2 input to 1. Is this operation reversible? It's not, right? So this matrix does not have an inverse because it's not a square matrix and therefore cannot be inverted. So this is not reversible. So we talk about unitary matrices, so we emphasize the fact that unitary matrices are reversible, but we didn't talk much about preserving the norms of probability. So the unitary matrices preserve norms and preserve in particular the sum of the modulus squares of column vector multiplied on its right. So this is a really key property if we express probabilities as the square of complex numbers and the sum need to be 1. In other words, if the sum of the probability that we have our vector that the sum up to 1, we apply a unit transformation, we want to have the sum of probability still equal to 1, right? We don't want to lose some probability when we apply this matrix. So unitary matrices are extremely important because they preserve the total probability of finding the quantum state, the system in a certain quantum state. Reversibility about also the fact that we preserve the norms of probability. So the sum of the probability is always 1, right? And we do not lose probability during the transformation. This was the last slide, and talk to you soon.